Hey everybody, I wanted to make a quick video about balancing redox reactions in acidic conditions. This is one of the first things in chapter 6 if you're looking in the textbook, Atoms First, Open Stacks. But I wanted to do it step by step, show you acidic conditions, show you basic conditions, and then a trick that I have for basic conditions. So these are the steps we're going to follow. We're going to write the half reaction. So right now this is the reaction we want to balance in acidic conditions. We're going to figure out how we write it in terms of two halves. We're going to balance the elements besides oxygen and hydrogen. Then, because this is an aqueous solution, all of our oxygens we can just balance with hydrogens. All of our oxygens we can balance with waters. And then since we're in acidic conditions, we can balance all of our hydrogens with H pluses. Then whatever we have left over in terms of charges, that we balance with electrons. So if I split this up into two half reactions, one of these is going to be pretty straightforward. It's going to be chromium solid, goes to chromium 3+, aqueous, and we're going to follow the same steps. I've got one chromium, so that's my known half reaction. My elements are balanced. There's no oxygens or hydrogens to balance, so I can just jump to balancing the charge. I've got one side that's neutral, one side that's positive. I need to add electrons, so I want to get rid of that +3 by adding a -3. So that's going to be 3 electrons. So that's the first half balance. That one was the easy one. Now let's look at what happens with this manganese oxide. So that was half 1, and then we'll look at half 2. The manganese oxide is going to go manganese oxide and manganese 2+. Okay, so the first thing we notice, this is our known half reaction. This is what we have informationally. We see the manganese is balanced. Then we say, okay, I've got to balance my oxygens. So I'm just going to add, the right number of waters. So each water has 1 oxygen, so I'll add 2 H2O. In doing that, I've now balanced my oxygens, making use of the fact that this manganese, this entire system is in aqueous conditions, which means there's water floating around, so I can just add water, no problem. And then since I'm in acidic conditions, these extra hydrogens I have floating around, I can take care of those by adding 4H+. Right? Since I'm in acidic conditions, I'm essentially in a situation where there's a bunch of extra H pluses floating around. So there's my 4H+ added in. The last thing I need to do is I need to balance my charge. Since this one was losing electrons, I'm expecting this one to be gaining electrons. So I'm expecting to have to add to my reactant side. I've got a +2 charge on my products, a +4 charge, because I've got 4H pluses, a +4 charge on my reactant side. So to get rid of those, that extra charge, I only need 2 electrons more, right? In this situation, I'll have a +4 - 2, that's going to give me +2 on my reactant side, and then I've just got my +2 and my 0, so just a +2 on my product side. So my overall balance for this one is going to be 2 electrons plus 4H plus MnO2 solid goes to Mn2 plus 2 H2O. I should have my states of matter. I was trying to be careful with my space, but you should always have states of matter on there. Okay, now to get my overall reaction, I need to have my number of electrons match. So I'm going to need an x2 on that reaction, so I end up with 6 electrons. I'm using a 2 to 3 ratio, like 2 electrons here, 3 electrons there. So 6 electrons would be the best. And then I'm going to have a 3x on this one. This part's the same we've seen with our other reactions, our other acid-base, our other redox balancings. We've had this like match the electrons. So the new part was this stuff in orange here. So I'm going to end up with 6 electrons plus 12H plus 3 MnO2 plus 2Cr. Now, I didn't have enough space, so I'm just going to go down. Pardon me. We're going to have 3Mn, 2 plus 6H2O plus 2Cr3 plus 6 electrons. Right, I've got 6 electrons, 6 electrons. I should cancel those out, right? That's not going to actually be around in the final result. I have them there so I can very clearly see 6 electrons is transferring from the thing getting oxidized to the thing getting reduced. Always a good idea to double check things afterwards. We could have done double checks along the way as well. I've got 12 H's, 12 H's, 3Mn, 3Mn, 6O2, 6O2, 2 chromiums, 2 chromiums. I've got plus 12 on my reactant side. I've got plus 6 and plus 6 plus 12 on my product side. That's balancing in acidic conditions. Now, basic conditions, we essentially just have to add a step. There's 2 different ways to do it. There's really only one way to do it, and then I'm going to show you the trick that I've been working on. So to balance in basic conditions, we're going to add an extra step. I'm going to call it step 4b for basic. So we'll do 4, and then we'll do 4b. First, I'm going to erase this and make space for the next reaction we're going to balance. So in this situation, where we're balancing in basic conditions, we're going to follow the same steps we have so far with one extra thing. And this makes it so we're not really learning 2 separate processes. We're learning one process, one kind of trick for balancing all these things, using our knowledge about how acids and bases behave inside of normal conditions and relating it to redox reactions. So if we're doing in basic conditions, we had step 4b, which is sorry, I had a little erase there. Let's call this neutralize. Right, we're going to add this neutralize step, right? In basic conditions, we can't actually add H+. The way I think about it is what we're really doing here with the H+ and the OH- is we are adding HOH, right, which is essentially water. That's the neutralization reaction. So that's how this trick works, is we are doing this neutralization step where we're getting rid of our H+'s with our OH-'s, or you can think of it in terms of step 4 as like balancing out our acidic conditions within a water in HOH. So let's look at how that goes with a different reaction. The reaction I have for this one is something we actually did in lab. O2 plus CN. Right. So this is our known reaction, the reaction we want to balance in basic conditions, very similar to something we did in lab. We'll see in a moment. You'll see O2 sometimes listed as gas or aqueous. This works whether the O2 is a gas or whether it's a gas dissolved into the water solution. You'll see 2 different labels depending on what conditions your experiment is in. We're going to do the same thing. We're going to follow our steps with this one extra new step 4b. Again, I picked this reaction, so again we have 1/2 that's a little bit easier. So we're going to have Zn solid going to Zn2 plus aqueous. And if we look at our steps, we write the known half reaction, we balance the zinc's already balanced. There's no oxygens to balance, there's no hydrogens to balance, there's nothing to neutralize. We just go all the way down to step 5, where we balance charge with electrons. So I can just go ahead and add my 2 electrons here. Then I want to go ahead, I want to look at the other half. And this one looks a little bit funny at first because we've got O2. I'm just going to call it aqueous for now. We've got O2 going to nothing. And you think to yourself, how can we have O2 going to nothing? Well, of course we can't have O2 going to nothing. We have to recognize that we're in aqueous conditions. This is going to be balance our oxygens with water. So we're going to go ahead and add 2 H2O over here. Right? Now I've balanced my oxygens. This makes a little more sense. My oxygen is going to something. Now I have to keep going. I ended up introducing 4 hydrogens. So I have 4H plus. Now, of course, I can't add H plus if I'm in basic conditions. So right away, I'm going to add 4OH minus as well. This makes it like I'm adding water. These are going to neutralize out. But I just balanced my oxygens, and I don't want to mess up that balancing. I just balanced oxygens and hydrogens. So I'm just going to simultaneously add 4 hydroxides to the other side. Now what this will do is it'll make it so my oxygen balancing and my hydrogen balancing don't get messed up, and I also don't end up in acidic conditions. I end up in basic conditions. When I put this all together, oh, I've got one more step. So this side is going to be overall neutral, this side is going to be 4 minus. Last thing I need is I need 4 electrons over here. Right, because I've got a -4 on my product side, I've got a +4, -4, +4 to get a -4 on my reactant side. Also, expecting this one to be gaining electrons because this one was losing electrons. So when I put that all together, I'm going to end up with 4 electrons. I'm going to put these two things together. Since that's a neutralization, that's just going to become 4H2O. 4 electrons plus 4H2O plus O2 goes to 2H2O plus 4OH minus. I can take one extra step. I can cancel out these extra waters. That 4 becomes a 2. So I end up with 4 electrons plus 2 H2O liquid plus O2 gas goes to 4OH minus. I can double check all of my balancings. 4 hydrogens, 4 hydrogens, 2, 4 oxygens, 4 oxygens, -4 on reactants, -4 on products. We're looking pretty good. Now, to put these two together, to get the overall, that's the new stuff. Now back to old stuff, where I want to charge balance. I've got 4 electrons gaining here. That means I need 4 electrons losing here, which is going to be an X2. So I'll end up with 4 electrons. H2O liquid, O2. I keep switching between gas and aqueous. Let's just keep it aqueous for now. Plus 2 ZN solid. Whoa, my 2 looks weird. My 2 looks too much like my Z. 2 ZN solid. Again, I'm just going to use the down arrow because I didn't give myself quite enough space. Products, I'm going to have 4OH minus aqueous plus 2 ZN2 plus aqueous plus 4 electrons. Again, we cancel out the 4 electrons, recognizing the fact that this means 4 electrons transfer from the thing being reduced to the thing being oxidized. Sorry, oxidized to reduced. Oxidation is loss, reduction is gain. And then I can go ahead and do the rest of my checking, make sure everything's balanced. I've got 4 oxygens, 4 oxygens, 4 hydrogens, 4 hydrogens, 2 zincs, 2 zincs. My reactant side is 0 charge. My product side is a -4 and a +4, so it also ends up overall 0 charge. And that's how we balance in basic conditions. We follow the same steps, and we use that little trick of the neutralization adding the HOH, right, doing this water step in order to balance it out. And that's how the textbook has you do it. That's how all of the online sources will teach you how to do it. That's how I've always learned to do it. So that works. Now, I want to show you something else that's been on my mind. And I think this is a different way to balance in basic conditions that for me makes more educational sense, but I'm not sure if it is as foolproof as the method I just showed you. I've only been working on this for a little while, and it's worked in every case I have done so far. We're just going to balance the same reaction and see how the steps are different. So we're going to look at the same reaction. Where did I put all my pens? Oh, it's in my hand. Okay, so we're looking at O2 aqueous plus zinc solid going to zinc 2 plus. First one's boring again. Zinc solid to zinc 2 plus 2 electrons. Okay, then we want to look at the second half reaction. That's going to be O2 aqueous goes to. And this one we're going to do things a little bit differently, right? So now when I go to balance the, there's no elements besides oxygen and hydrogen, so I'm going to balance my oxygens with double my hydroxide. So instead of putting water here, I'm going to put double. So I've got two oxygens, so I'm going to want 4 OH minus. Now, why am I doing 4 OH minus? So this is based off of the methodology we just learned, where we used water to balance instead of hydroxides. And the reason we used water was because we knew we're in aqueous solutions, right? Here, we know water is going to be the next thing we use, and water has a 2-to-1 ratio of hydrogens to oxygens. So I'm essentially using hydroxide to balance my oxygens and my hydrogens at the same time, knowing that I can fix it because I'm about to add water. So then I go ahead and I go balance my hydrogens and my oxygens with waters. So I've got 4 hydrogens, so I'm only going to need 2 H2O. And because I did double my hydroxides for balancing my oxygens, adding 2 waters doesn't mess up my oxygens, right? It balances out my oxygens. I essentially threw off my number of oxygens in a very predictable, controlled way. And now I can balance charge, right? So it was one step to do that. And then I can just add in, I've got my -4 on the product side. I need 4 electrons on my reactant side. So I added hydroxide in a strategic way, so that way I could do the waters next. There's no like neutralization reaction. There's nothing to cancel out. I end up with 4 electrons plus 2 H2O liquid going to 4 OH minus aqueous. So we get the same result that we got in the previous example, doing the traditional way of balancing basic conditions rather than doing this basic way of balancing in basic conditions. I'm reluctant to have this be the way you always do it. I'm worried that I'm forgetting something. I've never seen anyone else balance it this way, but it seems to work, and it seems to work in every case that I've tried. It does mean that there's a slight difference in the way that we have to think about it. It looks more like 2 different processes, but I find the mental connection between adding hydroxides in basic conditions rather than doing a neutralization reaction to be more cohesive to the thought process. Let me know what you think, either in office hours or in the comments, and we'll go from there. Good luck.